All right, well, I'm going to get started here. I hope you guys got a chance to study a little bit, for next Tuesday, right? Our first exam. Exam 1 is on next Tuesday. Well, this is the last lecture for you guys to ask questions before the exam. So if you guys don't have any questions, we'll move on to talk about floating point representation. So are there any questions from studying a little bit from between Tuesday and today? Okay, no question. Yep, go ahead.
Floating point number representation going to be on the exam?
Nope. That is not going to be on the exam. Any other questions? I like those questions that starts with, can I ask a question? Because, what if I say no? Then I will be self-contradictory because I already answered one question, right? So in order to say no or to mean no to those questions, I basically have to say nothing at all. It's like just turn away and pretend nobody asked the question. All right, so what we'll do today is to start to talk about floating point number representation. If you guys had a chance to read ahead of me, it'll be great. But I think if your math is okay, this is not going to be that big of a deal. Okay, it's actually in some ways easier than binary number comparison, for instance. Okay, yes, I believe so. So let me check. I specifically moved it into this workspace, so I can easily see whether it's recording. So it is definitely recording. All right, so we'll start with this module today. And if you look at the module, the first thing it does is to bring you to a Wikipedia page. Because I thought, hey, if Wikipedia already has the correct, accurate, and complete information, why do I want to replicate all the effort, right? Doesn't make any sense, okay? So instead of talking about, instead of repeating what is already there, I can just kind of summarize what a floating point number is. In this class, we're talking about the double precision IEEE floating point number. Okay, otherwise we'll just call it double. Okay, because otherwise it's a really long name. To say double precision floating point number using the IEEE standard. That's a long name, so we'll just use double. Okay. So a double has 64 bits. Okay, 8 bytes, and for the discussion of the format, we'll use these notations. Okay, f of I, to refer to bit I of a double. So we are basically talking about 64 bits, 64 binary digits, kind of stuck together. So the first one, or the least significant one, is going to be F0, and then all the way up to F63. Because if you count from 0, the most significant bit is now called bit 63 and not bit 64. So knowing that nomenclature, we'll start with the interpretation, but we'll do the interpretation from the most significant and work backwards. So we'll take a look at bit 63, which is the most significant bit in a double. It is called a sign bit, okay, and we know kind of what a sign bit does, okay. But in this case, the sign bit is on its own. It is completely independent to all the other bits. If the sign bit is a 1, it means the number represented is negative. If the sign bit is a 0, it means the number or the value represented is not negative. That's all, okay? But it is not a part of a larger integer, okay, as a sign bit. And then we go back a little bit. So now we talk about bit 52 to bit 62, okay? Because bit 63 is already the sign bit. We know what it does. So we back up 11 bits now. Bit 52 to bit 62 is an 11-bit number. It is treated as an unsigned binary number. In other words, the first thing you do is you figure out this particular value E. Let me highlight it. So this way you can focus on what we are talking about here. Do we have any questions about this notation? Looks a little awkward, okay? So we'll take a look at this. I is the index. It starts from 0. It ends at 10. So how many iterations do we have? 11 iterations. For each iteration, we produce a value which will be summed over to become our E. So each term is like this, f subscript 52 plus I. So when I is 0, we're referring to bit 52. When I is 1, we're referring to bit 53, and so on. What are we multiplying f52 plus I to? 2 to the power of I. So when I is 0, we are determining, do we have a 1? When I becomes 1, we use bit 53 to determine, do we have a 2? When I is 2, we use bit 54 to determine whether we have a 4 or not, and so on. So it really is just like the interpretation of an unsigned number, except it is offset, okay, by 52. Do we have any questions about bit 52 to bit 62? It's an unsigned number, and it's an 11-bit unsigned number. But the actual exponent, which we'll explain later, is not exactly E, okay? It is biased, quote unquote biased, by 1023. So the actual exponent of 2, which I would use E2 or E subscript 2 to represent, is E minus 1023. So the actual exponent can be positive or negative. But when we represent it in the bit pattern, it is always going to be an unsigned 11-bit pattern. So I will give you examples so that these will all be clarified later on. So that takes care of 12 bits, okay? Because bit 63 is a signed bit. Bit 52 to 62 are what we call the exponent bits. And now we have bit 0 to bit 51. So those in return, okay, we are getting to here. These 52 bits are what we call the fractional base 2 mantissa, okay? What do I mean by that? Well, the actual mantissa, which I represent as m subscript 2 here, is the following quantity. Okay, I think the 1 plus does not need to be explained, so I'll just explain the sigma notation. Once again, we have a sigma notation. This time I is going from negative 52 to negative 1. That's the range of I, the index variable. What are we summing over? Well, whatever is here. So when I is negative 52, I plus 52 is going to be 0. So we're using the least significant bit of a double to tell us how many 2 to the power of negative 52 do we have. But tech, that number is going to be pretty small. 2 to the power of negative 52 is a pretty small value. And you would be right about that, okay? Because we are talking about 1 point and a whole bunch of digits, and this is the 52nd digits all the way to the right-hand side of a not decimal number, is a binary number, okay? Because these are all in binary. We move it up by 1. When I equals to negative 51, what are we doing? We are looking at negative 51 plus 52, which means bit 1, and that will tell us how many 2 to the power of negative 51 do we have, and so on. Are we doing okay so far with that representation? So the notation is okay? Is everybody kind of familiar with the sigma notation by now? Okay, and it only involves indexing into which bit we're talking about and a power of 2. Is that okay? So this is really a whole bunch of gibberish until I give you an example. So one way to represent the value represented by all of these things is v of f. Okay, so I'm just using v of f to represent the value represented by these 64 bits. First of all, we look at the sign bit. S is the sign bit. If the sign bit is a non-zero, then we use negative 1. If the sign bit is a 0, then we use a 1. Once again, I'm using a ternary operator. We have already talked about the ternary operator in this class, so if anyone is still not familiar with the ternary operator, it really is time to study it. Okay? So what do we multiply this negative or 1 to? Negative 1 or 1 to? We are multiplying that to the mantissa in base 2. The mantissa in base 2 is always between 1 and 2, excluding 2 itself. Okay, it is always greater than or equal to 1, but it is always less than 2. That's what M2 is going to be. And then we multiply that in return to 2 to the power of E2. What E2 are we talking about? This E2 over here. So we use bit 52 to bit 62, interpret it as an unsigned number, subtract 1023 from that. That becomes the actual power that we'll raise to 2 as a scaling factor. Is that okay? Does that look kind of complicated? Maybe, maybe not, okay? How many people know how to use base 10 scientific notation? Okay, the majority of the class, very good. So there's an analogy to that as well. So let me give you an example of a 64-bit floating point number, and then we'll do it in both directions. Okay, I'll give you the bit pattern, and then we'll convert it into the value it is representing, and then I'll give you a value and then convert it back into the double representation. We'll choose 2 different values. Okay, so hopefully that will kind of illustrate what we mean by all of this stuff here. All right. So to do that, I'm going to make use of just a text editor. This is just an example. I'm using a text editor for that purpose. And which way do you want to do it first? Do you want to start with a 64-bit pattern to figure out the value it is representing, or do you want to start with a value that we want to represent and then turn it into the 64-bit double representation? The first or the second? Okay, I think we got more seconds than first. Okay, it's okay. I mean, I'm going to cover both anyway. Okay, so the second one is we start with the value, and then we want to convert it into the 64-bit representation. So we'll go ahead. I'm going to choose a value that is easy to work with. Okay, to make it easier on myself. So let's try 4.625, and let's even make it negative. Okay, so this is the value. So V of F is this, okay? And then the question is, what is F? What is the 64-bit double representation of the value negative 4.625? That is the question. Okay, so we'll go ahead and try to answer the question. The first thing we need to do is to express this entire thing back into the format that we saw earlier. Let me show you what format we are talking about here. So where is that? Right here. So I'm going to scroll this up so that we can see that as we work out the math here. Okay, there we go. I think that works out okay. All right. And my battery is running low, so let me plug in the adapter. So I want you guys to kind of think about this a little bit. I want to express negative 4.625 into that format. So our job really is to find out what is S, what is M2, and what is E2. Okay? So go ahead and kind of think about it a little bit, and then after I plug in my adapter, then we'll come back and work on this one. All right, your time is up. What's the answer? All right, first, what do you think is the sign bit? Sign bit is going to be a 1 because the value being represented is negative. Very good, okay? So I'm going to explain that because V of F is negative. Okay, that's easy. What about M2? Well, M2 is a little bit harder, right? 4.625 does not meet the requirement that we want because we want M2 to be the mantissa and the requirement is it has to be expressed in the format of 1 point blah, 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 blah in base 2, which means it has to be greater than or equal to 1, which is fine because 4.625 is greater than or equal to 1. But it also has to be less than 2. Well, 4.625 is definitely not less than 2, is it? So we have to kind of play with that, right? So we'll work with M2 and E2 at the same time. So we have E2 and M2, on the same row. So at first we go like, well, I just want to be lazy. I want to use 4.625 as my M2, and then E2 is going to be 0, right? Does that make sense? Because if M2, which is not really quite playing by all the rules just yet, but if it is 4.625, then that is my value. I don't need the 2 to the power of E2 to have anything to affect the actual value. So what we do, we just turn E2 into a 0, so that 2 to the power of E2 is 1, and multiplication by 1 is the identity. It doesn't affect the value. Is that making any sense? It's my starting point, okay? We're not quite done yet, but it's a good starting point. Then we go like, but this is not going to work because M2 is still greater than 2, greater than or equal to 2, so we'll divide it by 2, okay? So if you divide 4.625 by 2, you end up with 2.375? No. 3.175? Like that? Okay. Well, if you divide the M2 by 2, don't you think you have to make up for that? Because I just divide one part of the number by 2, so what do I need to do to the other half, to the other side? Multiply by 2. Well, if I want to have the effect of multiplying by 2, but I can only play with E2, what am I going to do to E2? Make it 1. Very good. Okay. So are we still convinced that using this pair of M2 and E2, we really get the same value back? We're just playing with numbers here. Is that okay? All right. But M2 is still not meeting that requirement, so that means I'm going to have to divide it one more time. M2 is going to be 1. My math is so bad. And then it's 125 divided by 2. It's going to be 625. And over here, we got E2 equals to 2. Yay! We got one milestone done because M2 is now less than 2. But wait, M2 is supposed to be a binary number. This is base 10. How do we know this is base 10? Has no suffix, has no number in parentheses right after that. So it is implicitly a base 10 number. Okay. How do we convert M2 into a base 2 number? Well, you express M2 as 1 plus, do we have a quarter? Or do we have a half? We do not have a half, right? Do we have a quarter? Nope, I don't think we have a quarter. Do we have an eighth? Yeah, I think we got 1/8. Is that okay? So after the eighth, we have 2. Oh, my math is so bad. 2, 1 something. So the next one down, okay, I have to cheat a little bit here. I'm going to cheat. By using a spreadsheet. Oh, that's not a spreadsheet. That's my writer. That's actually for my other class. I need a spreadsheet. Okay. Calc. There we go. All right, so we have to look at 1.15625. And then on the other side, we have powers of 2. Okay, so start with the exponent is 0. And then over here we have 2 to the power of that. So power 2 to this amount here. Oops. And then we can have a question to ask, is this number greater than or equal to this power here? So we basically do a comparison. Is this number greater than or equal to this particular power of 2? It is true. And if that is the case, okay, if this is true, then we want to subtract this much from this much. So we want to have this number minus this number. Otherwise, we just want this number back. Is there already? Okay, good. All right, so with these 5 rows, okay, once again, A is the remaining portion of the value to convert. B is the exponent of 2 that I'm paying attention to. C is 2 to the power of the exponent based on column B. D is whether column A is greater than or equal to column C. And then E is, if that is the case, we subtract that particular power of 2 from column A. If not, we keep the entire thing. Okay? So this is how you calculate change, kind of like that. Okay? So now the next row, you might think, oh, but the next row is going to look pretty ugly. Nope, next row is going to be easy peasy. Because we start with whatever amount is left over. We move the exponent down by 1, which means it's going to be this number minus 1. And then this one we just copy. This one we just copy. And then this one we just copy. Well, let's take a look at this row 2 and find out what it means. Okay? The remaining portion to convert is 0.15625. And this particular row only deals with 2 to the power of -1, which we know as 0.5. There's no 0.5 in 0.15625, so we do not subtract that. We retain the entire amount for this row. Is that okay? What do you think the next row is going to look like? And how much time do you think I need to spend on the next row? It depends on how fast I can click. 1, 2, 3. And go like, that doesn't look like a binary number to me. Or we still have values to convert. Let's just go down a few rows like that. I'm done with my conversion. So what is this telling us? It's telling us 1.15625. Okay, the original number has 1 1. Okay, true, has 1 1, has 1/8, has no 16th, has 1/32, and that's it. Are we good so far? Don't you like spreadsheets? I love spreadsheets. It's kind of like a calculator, except a lot more flexible. Did you guys know that a spreadsheet can do conditional stuff? No? Now you do. And the conditional thing that I did here, okay, let me just kind of point out again. How many commas do we have inside the parentheses? Can you guys read all the way back there? Maybe? We got 2 commas, right? So that means there are 3 items. The first item is a condition. The second item is the value to use when the condition is true. And then the third item is the value to use when the condition is false. Haven't we seen something like this just minutes before this whole thing? The ternary operator. It's the ternary operator, except it's called an if formula in a spreadsheet. It is available in Excel. It's available in LibreOffice. It's also available in Google Spreadsheet. This is a very common feature in a spreadsheet. Are we good so far? So now that I have this little cheating thing, I can now say there are zeros of 0.0625 plus, okay, I just need to move it a little bit here. The next one, there's 1 of 0.03125, like that, and that's it, because everything else is going to be false because I don't have any values left to convert after this, okay? So I'm going to move this over to the other side. Then you look at this and go like, but Tech, this is not a binary number. These are all decimal numbers, base 10, except for the zeros and the ones, right? So let's see how we can do this conversion, okay? There's a 1 here, and I'm going to say 1 of 1. And here, oh, actually, I'm going to skip a step here. If you guys don't mind, I'll skip a step. And there's a 0 of 2 to the power of negative 1. There's a 0 of 2 to the power of, come on, you guys can sing along. I'm not singing. Negative 2, right? Plus 1 times 2 to the power of negative 3. This gives me that kind of eerie feeling of Sesame Street. This is what? Negative 4. And this is negative 5. I feel like the Count in Sesame Street. He's actually one of the, I was originally, afraid of that character in Sesame Street. Whenever he appears, in the Sesame Street, I have to turn off the TV. I mean, are you kidding me? He's a vampire. All right. Still doesn't look like a binary number. Okay. So now we do the conversion. 1 is 1 in base 2. Okay. This is 0.0 in base 2. This is 0.00 in base 2. This is 0.001 in base 2. This is 0.0000 in base 2. And this is 0.1234 in base 2. Oh, now we are starting to see some base 2 numbers. Do we understand this conversion? How I switched from base 10 to base 2 once I have, oh, there's 1 of this, 0 of this, 1 of that, 1 of that, 0 of that. But all of those, okay, each one is a power of 2. Once I get to that point, I can do the conversion. Because the number of places to the right-hand side of the binary point is telling you how negative of the power it is. So if I did have a half, it's going to be a 0.1 in base 2. Okay? Because that 1 is representing how many base to the power of negative 1 do I have. Is that okay? Are we? Yes?
Yeah, can you use the spreadsheet, the true and false, and the ones and zeros?
Yes, indeed we can. So if I bring the spreadsheet back, you will see that the spreadsheet basically expresses the same thing. So we can see that there's 0 of half, 0 of quarters, 1 of eighth, 0 of 16th, and 1 of 32nd. So yes, so the true false are actually digits in the binary number already. It's just that I did not express it as such. So that was good observation. All right. So now that we have the number that looks like this, I can just add up all of these digits. There's no carry or borrow to be concerned about because each column can only have 1 1. Okay, it cannot have 2 1s. So we don't have a situation where carry can possibly happen. So it's 1.00101 in base 2. Yay! So we got M2 already. We got E2. Oh wait, E2 doesn't quite translate to what we need. What do we need again? It's biased, right? So E2 is the biased version of the exponent. It is already biased by 1023. So we have to undo that subtraction of 1023 in order to go back to E, which is what we need to represent in bits in a double. Okay, so we'll go back to do that. So we'll say E is E2 plus 1023. So in this case, it is 2 plus 1023, which will give us, whoops, I forgot the 3 here, 1025, right? I think I can do this math. Is that okay? But 1025 is not a binary number. I need to express 1025 as a binary number. That is easy peasy. Why? Because 1024 is a power of 2. And this is just one off from it. How many people knew right away? It's like, oh yeah, I know 1024 is a base 2 number. Okay. Now 1024 is a particularly useful power of 2 because it is very close to 1000. So this is how you can estimate how many binary digits is needed to represent a particular quantity. Yes?
Yes. Can you go over how do you go from going to E2, line 14, to 2?
Okay, so let me switch back to the browser because it is actually in the browser here. So the browser talks about how E is calculated like that, which is basically just an unsigned interpretation of the bits. But the actual exponent of 2 is E2, which is E minus 1023. So we now have E2. We start with E2 being 2, but we want to figure out what is E, because E is what is actually represented in a double. Yes?
Professor, why do we just E2 if we put, for example, make M2 right away from 4.625?
Because M2 has an implicit requirement of being less than 2. And 4 point something is not less than 2. So we have to scale the mantissa so that it is between 1 and 2. But by scaling the mantissa to be between 1 and 2, we have to keep dividing something by 2. That's why we have to adjust E2 from 0 and up, in this case, to 2. Are we good so far? Can I answer a question back there? No? Okay. All right. So back to our example. So this is 1024 plus 1. And this is 2 to the power of 10 plus 2 to the power of 0. So I'm going to skip a bunch of steps here, if you guys don't mind. So it's 1 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 in base 2. I'm sorry if I just kind of skip a few steps, but it's conversion to base 2. Well, let me double check because my keyboard is particularly bouncy, so sometimes it will give me extra characters. We got 1, 1. Okay, that's the 1. 2, 4, 6, 8, 16, 32, 64, 128, 256, 512. Okay, I'm off by 1. Huh?
No, you're fine. You said 2, 4, 6, 8.
Oh.
Yeah. You're fine.
So let me count again. 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. Okay, now it's right. Okay, so it was right. I just counted incorrectly. Okay. All right. Yes.
So is it being added because the sign bit's a 1?
The sign bit is 1. Yes. So the sign bit takes care of the sign of the entire value. So the mantissa doesn't need to express that sign anymore. Okay? That was a good question. Anything else? No other questions? All right. So we got a whole bunch of bits now, right? We got a whole bunch of 1s and 0s. Where is the sign bit? It's all the way to the left-hand side, right? Bit 63. Okay. So we'll put the sign bit here. Okay. So I'm going to put sign and then put a 1 here. What about those 11 E bits, okay, the exponent bits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What do we put those? Those are bit 52 to 62. We can just copy and paste that stuff, right? Okay. So we have all of this stuff here. What about the fractional mantissa bits, which I call the M bits, okay? What about those? What do I copy over there? We know that we got it computed. The question is, what do we copy? Well, let's go back to the notes again, okay? Because this is actually quite important. So we go back to the notes, okay? And then we look up the mantissa bits, which is discussed over here. So it says right here, we got bit 0 to bit 52, bit 51, but this 1 plus is actually not a part of the representation in a double. Do you see that 1 plus being conditional to any bit inside a double? Is it multiplied by a f underscore something? Nope, it's there, right? It is unconditional. It is always there. So that means the 1 point of the mantissa is not represented in a double. It is always implicitly there. Okay? The bits that are actually in a double is only responsible for the fractional part of M2. So let me switch back to the example that we are doing right now. So our current M2, okay, which is the actual mantissa, is 1.00101. Okay, we got that figured out. But the 1 point is not represented in a double. We only copy the fractional part of the mantissa over here. Are we doing okay so far with that? Because every mantissa, okay, if the rule is M2 has to be greater than or equal to 1, but less than 2, don't you think every single mantissa M2 is going to be 1 point something? Then why do I want to waste 1 bit to represent that 1 point? Is that making any sense? So it's not really just a rule. You kind of have to understand why that rule exists, okay? Because we don't want to waste that 1 bit. So now we just copy 00101. Oh, we are running out of digits. What am I going to do with the rest of the bits? They're all zeros. Okay, so we just a bunch of zeros after that. All right, well, I claim that this is the double representation of the value negative 4.625. Are you going to buy that? I mean, you pay for your units already, so obviously you bought it. Yep.
Professor, so we didn't put anywhere our E2, right?
What? Say it one more time.
Oh, no, never mind. I got it.
Okay, so obviously you're not going to buy this, okay? You're going to have to say, Tag, you have to prove it to me, okay? Show me that this is actually the value represented. So now I have to figure out a way to do it. So I'll show you how I will demonstrate this. It's actually a very interesting process. I like this process. Okay, can you guys read this? Is it big enough to the people in the back? Okay.
A little bigger.
I can make it slightly bigger. Would that work?
Yep.
Okay. So I'm going to go make a very simple program. I can do it in temp. We'll just call this simple. And simple is actually very simple. The only thing I do need that is not so simple in simple is I'm going to include stdint.h. If you do not know what it is, it's a good idea to start to learn what it is. If you have not used it in your other classes, it's a good time to start using it. It stands for standard integer.h. It's a header file to define integer types. Then you go like, I learned integer types from cisp310. Some of you have taken 400, 430 already. And you go like, I have no need to have something like that. Well, until this class, you may not have the need to have to specify. I don't just want an integer. I want a 64-bit integer. Because if you just say int I, okay, how wide is that I? How many bits is that integer? It depends, right? If you're using GCC on a 32-bit system, int is going to be 32-bit wide. On a 64-bit system like this, I suspect it's 64-bit. but there's no sure answer to that question. If you're cross-compiling to the AVR platform, which is the same kind of processor used by Arduino, int is 16-bit wide. So it varies, right? Why would that bother you in any way? The range of values that it can represent is changed. A 64-bit integer can only represent negative 32,000 to 32,000 something. That's the range of a 32-bit integer. 32-bit integer can represent everything from negative 2 billion to positive 2 billion something. Okay? 64-bit integer, obviously, we have a lot more range of values that we can represent. Then you guys might think, but I will never run out. My loop only needs to go from 1 to 100, for instance. Okay? So I don't really need to care. Well, in this class, in classes like this, you may not need to deal with larger values. But when you're dealing with robotics, for instance, and you're dealing with acceleration, displacement, that sort of stuff, you might be able to run the numbers up to, you need to consider the range of values that can be represented by an integer. Is that making any sense? All right? So the danger of not knowing how wide an integer is it may work on one platform and it may not work on another platform. Same source code, same compiler, GCC, but because you may be cross-compiling to another architecture, that changes the width of integers. Then you'll be scratching your head and go like, but it's the same program. It worked here, but it's not working here. And why would you encounter situations like that? Because your development environment may be a larger, more powerful system. Okay, you have an i7 system in your test platform for a robotic system. You have 64-bit integers. So all your displacements, everything, can be well within the range of a 64-bit, what a 64-bit integer can represent. Then in production, your boss says, we cannot have a $200 processor on a $40 robot. Okay, you go, okay, we have to downsize then. Oh, we can downsize to the same processor as a Raspberry Pi. I heard that is relatively inexpensive, right? So yes, okay, so it turns out to have enough processing power, and then you just say, okay, we'll just port the code that was running with an i7 processor system, the development system, onto the production system, which is running the ARM processor. The ARM processor is inherently a 16-bit processor, but it's considered as 32-bit processor. So suddenly your integer changes from 64-bit to 32-bit. And that may just shrink the range of values that can be represented to break your program. But only when the displacement is up to a certain range. So your Roomba will now work as long as it is within 6 feet of the base. Beyond 6 feet, your Roomba goes crazy. But in the development platform, everything works all the time. How are you going to debug that program? You don't want to debug that program. You want to prevent that from happening. This is why we are doing this. So by including standard integer.h, I can now use uint64_t as a type to basically say, I know this has to be 64-bit wide. Okay? So I'm going to call this x here. Okay? And I have to do something with x. Otherwise, it gets optimized out of the program because of the smartass compiler. And this is my entire program. And you go like, it doesn't have anything to do with doubles. How can this program possibly help to explain doubles and to verify that the program, not the program, but the numbers, the digits that we just figure out works? Well, I'll show you, of course. So we say GCC, okay, if you have not used the command line to compile a program, it's really a good thing to learn. We used to have to do this in this class, for the entire semester. But since I changed to my own architecture, which does not have any GCC tools to support it, we don't have to do that anymore. So GCC-O, to specify the executable. Typically, you want to turn on all the warnings. which is W, the first W. The uppercase W means warning, and then this is basically saying turn on every single warning available. Okay. Okay, I think that's it. Apply the. So it gives me a warning. It says variable x is set, which means I assign a value to x, but it was never used. Okay, it was never read. Okay, it's just okay. It's not a big deal. All right. So oh, I forgot one thing. I forgot to specify dash G to specify debug. Okay, so now I'm including debug information into the executable. So I run gdb to debug the program. Okay, like so. And I list the program, put a breakpoint on line 7. Run the program. I want to print the value of x. Okay, it's 0. It has absolutely nothing to do with doubles, right? So here's the part that is going to make it fun, okay? So what I want to do now is I want to turn this entire bit pattern into a 64-bit integer. Is that okay? So kind of imagine that I filled in all of these extra zeros so that we actually have 64 bits. And I want to take that binary number and put it into x, the variable x in main. I have several problems now. GCC does not understand binary. So there's no way for me to copy and paste it. And 2, even if it could, that's a lot of digits, right? 64 digits, that's a lot of digits to copy and paste. So the solution to that problem is base 16 numbers, otherwise known as hexadecimal numbers. Hexa is 6, deci is 10, so when you combine those two, what do we get? 16, base 16. All right. So when you're dealing with base 16 number, the first thing you need to do with a binary number is to pack it into blocks of 4 bits. Okay. So we we say, okay, 1, 1, 0, 0 is one block. 1, 2, 3, 4, that's one block. 1, 2, 3, 4, that's another block. That's another block. Another block, another block, and a whole bunch of zeros after that. Okay. Okay, so now it's still binary. I don't see any hexadecimal digits here. So what you need to do now is to come up with a way to convert base 2 to base 16. And most people are thinking, oh, not one of those base conversion things again. In fact, we're skipping base 10. We're converting from base 2 to base 16 directly. Skipping base 10. There's no multiplication, no division, no mod, and stuff like that, because you can use a lookup table. Okay, so I'm going to show you that too. All of these are tools that will come in handy for every programmer. Okay, so I'll show you how to do this. 0, 0, 0, 0. How do you think I should represent it in base 16? Are you sure? Are you sure 0 is really 0 in base 16? Yes, it is. And 1 is 1. 1, 0 is 2. 1, 1 is 3. 1, 0, 0 is 4. 1, 0, 1 is 5. 1, 1, 0 is 6. That's 7. That's 8. I mean, you guys know this already, right? I mean, we did this with the number wheel many times. Yeah. So no surprises here. 9. Okay. I think up to this point, we should feel familiar with these conversions, right? Then here comes the next one. 1, 0, 1, 0. Oh, it's 10. It is 10. The value is 10, but we do not write down 1, 0. Because it is base 16, we have a digit, a single digit, to represent the quantity of 10. And what do you think it is? A, exactly. We borrow it from the alphabet. This is B. That's C. That's D, E, and F. So we use up all the digits from 0 to 9 the way they are intended, just like in base 10. And then we borrow 6 letters from the alphabet. So we borrow one A to F to represent the quantities of 10 all the way to 15. So if you want to, the next exam 1 is not going to need this, okay? For exam 2, you probably need this. So if you don't think you can memorize all of this stuff here, make a table, print it out, you put it into your notes. Okay, it's just a table lookup. So with this table lookup, I can now go back to my bit pattern. Okay, and now we say, oh, we got a 1100 here. What is that? Look up the table. C. Okay, very good. 0000, just a 0. 0001, it's just a 1. That's a 2. That's a 8. And then we have a whole bunch of zeros. How many zeros? Well, let's count. Each hexadecimal digit is representing exactly 4 bits. So we have figured out, including this 0 here, we have figured out 1, 2, 3, 4, 5, 6 digits. How many digits do I need to make up 64 bits when each digit is 4 bits? 16 of them. So I got another 10 zeros to fill in, right? Okay, so that's one way to do it. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So now I can take this number and just copy it into my debug window. Okay. Let me concatenate everything first so it's easy to copy and paste. So I'm going to use 0x. What is that? It's the prefix to mean what follows is a hexadecimal number. Because if you do not have a prefix to indicate what follows is a hexadecimal number, then 100 can be 100, but it can also be 100 in hexadecimal. There wouldn't be a way to tell which way it should be interpreted. So 0x is a prefix that says what follows is a base 16 number. So now we have C, 0, 1, 2, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, there we go. So I take this number, copy it, switch to my debug window here, and I say set, variable x to the following value. Takes it without a problem. Print it out. And everybody wants a refund for the money that you pay for all the units of this class. It's like that doesn't even look like 4.625 or the negation of that. Well, that's because it is interpreting those bits as if it is a unsigned 64-bit number. Of course, it's not going to look like 4.625, right? So how can I make a C environment to look at those bits as if and interpret those bits as a double instead of an unsigned 64-bit number? And some people may remember a certain operator in C and C++ called typecasting, right? Well, let's see whether that works. So we say double. Okay, look at x as a double. It still doesn't work. Why is it not working? Because x itself is an unsigned 64-bit integer, right? And what double is telling the compiler or the environment to do is to say, well, the value is 13840 blah blah blah, but print it out as a double. That's what it did, because it prints it out as a scientific notation, 1.38 blah 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 times 10 to the power of 19. That still doesn't work. So no, that is not going to work. So this trick will work. So I will work this way backwards. Okay, this is x, right? What is that? Is the address of x, right? Which is a location. It's a pointer, right? What is the type of ampersand x? It's a pointer to an unsigned 64-bit number. But pointers can also be casted, can't it? Right? So I'm going to cast this to that. What is that telling the compiler to do? I have an address here, okay, which is just a location in memory, right? Which originally is the address of the first byte of a 64-bit number, okay? You can kind of look at it as this is the address of a residential, property, okay? The cast is basically saying it is still an address, but it's not the address of a unsigned 64-bit number anymore. Now it is the address of a double. Okay, it's still the same address, but it's not residential anymore. Now it's commercial. Okay? And the UPS driver says, I cannot deliver at this price to a residential address. Oh, wait, it is now a commercial address. I can deliver now. That's what it is doing. Okay, it's casting the address, not the content. So what do you think I need to do to look at the content inside this property as if it is a commercial property? Dereference, right? And what is the symbol for dereference? Asterisk. Very good. All right. So we'll give it a try. Woo. We get our negative 4.625 back. So that's the trick. Okay. So this demonstration itself is actually including several tricks. Hexadecimal number representation, okay? Casting, but not casting the value, but casting the address. And then you interpret. So you cast the address, and then you ask the question, what is there? Is that okay? Cool. I think it's pretty cool. All right, but connecting back to what we were talking about in class, hey, it works. Okay, the conversion process actually works. So, are you guys ready to go the opposite way? I give you the binary representation of a 64-bit double, and then we'll try to figure out what value it is representing. Are we good with that? Okay. So we'll switch back to here. And this time I'll give you a value. Okay, so we'll say 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we'll have that. And then we'll have, just 1 over here, and then a bunch of zeros. Okay. So this is the bit pattern that I'm giving you. It basically, the most significant bit, or bit 63, is a 1. And then we have 1 followed by 8 zeros, and then 1 0, and then 1 1, and then a whole bunch of zeros all the way to the right-hand side. Okay? So right away, we have to kind of chop it up into the portions that we need, which is kind of already done. I specifically put a space in between so that it's easy to tell. This is our sign bit, and these are our E bits, and the rest are the fractional mantissa bits. Is that okay? Are we okay so far with how we dissect the bits into the 3 portions? There's the sign bit, the exponent bits, and the fractional mantissa bits. Are we good so far? Okay. So now we look at the sign. Okay, the sign says it's 1, so that means it's a negative number. That's easy to figure out. So what is E? E itself is the unsigned interpretation of those 11 bits. And by those 11 bits, we're talking about these 11 bits, right? So what is the unsigned value of those 11 bits? Yeah, we have to change it back to decimal. What is it? You have 5 seconds to... No. 1026. Very good. Okay. So E is 1026 because we have no 1, we got a 2, and then blah, 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 blah. We have 1024. 1024 plus 2 is 1026. Okay? Okay. If E is 1026, what is E2? Remember, E is a biased representation of the actual exponent. 3 is correct because E2 is just E minus 1023, which turns out to be 3 in this case. Are we good so far? All right. What about M2? Okay, now I'm not talking about M, I'm talking about M2, which is the actual mantissa. Oh, we have to start with 1 point, okay? Regardless of the actual bits inside the double, M2 is always 1 point something, because what is included in the double itself would be the fractional part of the mantissa. Is that okay? So what bits should I copy over to just to the right-hand side of the point? Just a 1, 1, and then a bunch of zeros. Okay, I'm just going to say 1, 1 here. Okay, it's 1, 1 in base 2. Okay, we got all the components. So the exponent of 2 is 3. The mantissa is 1.11 in base 2. And the sign is negative because the sign bit is 1. So we are really close to figuring out what value it is representing. Okay? Yes?
You said the 1 is 1 point is given, right? And then the 1,
Yes.
1, 0, 0 is the everything.
It's the fractional part of the mantissa.
So you only worry about the fractional part.
Yes, we only represent the fractional part in the double. Yep. Okay, but what is the value here? Well, this one is representing a half. This other one is representing a quarter. So together we have 1 plus a half plus a quarter, which is 1.75. And because we are multiplying this to 2 to the power of E2, in this case it's 2 to the power of 3, which is 8. So the answer is going to be 1.75 times 8. Okay, whatever that is. But there's another way to look at this. Okay, so I'm going to give you another way to look at this. So this time I'm going to look at it like this. Okay, I'm looking at E2, which is 3 at this point, and I'm looking at M2, which is 1.11 in base 2 here. So instead of messing around, with the mantissa itself and come up with some fractional stuff, let me see if I can do something like this. If I change this to a 2, how should I re-express M2 so that the product between E2 and M2 remain the same? What should I do? Double it, right? Double it. Because by decreasing E2 by 1, I'm halving the exponent portion. But in order to compensate, I have to double the mantissa. But to double the mantissa, I can just move the binary point. Are we buying this? Well, there are several ways to think about this. The binary point is really just a separator, separating the quantity of 2 to the power of 0 from 2 to the power of -1. Okay? So you have to ask yourself, is 1 plus 1/2 plus 1/4 really half of 2 plus 1 plus 1/2? What do you think? It really is the same, right? The first is 1/2 of the second. Well, we still have 1 digit to the right-hand side of the binary point. Let's do this one more time. Is that okay? I'm just moving the binary point again. We're good? But now I don't have a fraction to deal with, because 111 in base 2 is just 7. This is just 7 in base 10. So the value represented by this particular floating point number is -1 times, because the -1 comes from the sign being a 1, times 7 times 2 to the power of 1, which we know as, hey, it's just -14. So -14, I claim that -14 has a bitwise representation like this in a double precision IEEE floating point number format. That's my claim. How do we check this? Well, we have to do it, well, we can do it the same way as before, okay? But we can also do it in a slightly different way. In other words, we put negative 14 as a double into the 64-bit unsigned integer, and then we look at the bit pattern. How about that? Would that work? So we are reversing the process in GDB to double check the answer of this one. Would that work? Huh? Double check, yep. Okay, so we go here. So this time we say set var. So I'm doing exactly the same thing, except this time I'm changing this location as if it is to represent negative 14 as a double. Is that okay? So the right-hand side of the assignment operation is negative 14, but I make sure it is not the unsigned integer 14, it is the double representation of 14. And I'm going to store that to the left-hand side. What is on the left-hand side? The left-hand side really is the home of a unsigned 64-bit integer. But I told the postman it is not. It's the same address, but it's not the same person. Is that okay? So the assignment would occur without a problem. Okay, press the Enter key. That's fine. And then I can print X here and go like, no, that doesn't look like what you claim it to be, Tech. Well, because we are looking at a decimal representation. They go like, okay, what else can we do here? This is not telling me the bit pattern, not easily. I cannot tell the bit pattern easily from the base 10 representation. What should I do now? Now this is a very trick question, so let's see if you guys get tricked. What should I do now? How do I convert a base 10 representation into a way so I can look at the bit pattern more easily? Hexadecimal. You got tricked. Because, well, this is me being very tricky, because in GDB, it can actually print in binary. C cannot understand binary numbers, but GDB can print values in binary. So that's why I said it's tricky, because I knew that, but you did not. Okay, does that match what we were working on? I cannot remember. I have to check. Okay, so let's double check here. We got 1100, right? Okay, 1100, and a bunch of zeros here, and then 1011, and a bunch of more zeros after that. So that worked out.
Can you print in hex?
Hmm?
Can you print in hex?
Can I?
Print in hexadecimal?
I can certainly print it in hexadecimal. Okay, so before we print it in hexadecimal, let's try to figure it out first by hand. Then we can check whether the process works okay or not. So remember, we have to chop it by 4s, right? So these 4 would be a C. Then we have a 0. Then we have a 2. And then we have another C. Is that okay? So it would be C, 0, 2, C, and then a bunch of zeros after that. Okay? So we'll give it a try. C, 0, 2, C, and a bunch of zeros. But this really helps to illustrate why hexadecimal numbers are useful. Because one, it is very short. It's shorter than the base 10 version, not by much, but just a little bit shorter. But the second one is you can very quickly go from hexadecimal back to the binary representation. Now, why would that be useful other than this class? Because only odd people like tech likes to work with binary numbers, right? Nobody else wants to work with binary numbers. How many people have taken a networking class? Okay, I'm so disappointed. How many people have worked with networking at home, setting up your net mask and stuff like that? Do you remember the net mask is always 255.255.255.0? Where do you think that 255 comes from? 255 is FF in hexadecimal, which is a binary number of 11111111. Yep, so a net mask is binary based because it is trying to tell you, because each IPv4 network address is 32-bit wide. But of the 32 bits, you can designate some bits to be what we call the network address, and then the other bits would specify the interface address within the network. So the net mask is trying to tell the router which part is the network address and which part is the address of individual components inside the network. And it's bitwise. What about MAC addresses? Has anyone ever tried to spoof a MAC address so you can gain network access at a certain place? No. We're all honest people, right? We will never spoof MAC addresses. What does a MAC address look like? There are how many digits in a MAC address? There are 6 digits. What do they look like? 0 to 9, A to F. They are hexadecimal digits. That's a quick way to represent a bunch of binary digits. So we do use hexadecimal numbers actually quite a bit.
Like color
Hmm?
Like color hex codes?
Like
To get a specific color when you're drawing?
Yes. So in HTML, you can use 6 hexadecimal digits to represent RGB components of a color. Yes. So it is really quite useful. Okay, it's beyond this class. There are applications of hexadecimal numbers, binary numbers, and so on. Cool. So at the end of the day, what exactly is a floating point number? It has 3 components, right? So if you really want to just understand the concept of what a floating point number is, the 3 components is easy to understand. One is the sign, okay? One specifies a quantity, and then the last one specifies a scale. That's basically it. Quantity times a scale, which is always a power of 2, and then 1 extra bit to tell you, oh, is it positive or not positive, negative or not negative. And that's it, which is no different than scientific notation in base 10. Okay, so let me see if you guys understand scientific notation in base 10. 1.23 e negative 16. Okay, what does that mean as a scientific notation in base 10? Hmm? A lot of zeros?
Yeah.
Well, it is 1.23 times 10 to the power of negative 16. It's 0 point, a whole bunch of zeros, 1, 2, 3 somewhere. Well, it's 0.15 zeros and then 1, 2, 3. Yep. But it's the same thing. The double representation is really exactly the same thing. You have the sign bit. You have one component to specify the scale, which is the E, the exponent part, and then you have the mantissa part. So the only tricky part, let me just re-emphasize what parts of a double is tricky. So the tricky part is the exponent is biased by 1023. So what you see as a binary representation is the biased unsigned version of the actual exponent. It's biased by 1023. So somebody may ask the question, so why don't they use the signed representation of 11 bits? I cannot answer that question. This has been decided already. Because they could have done that already. They could have just said, well, we'll use 11 bits, and then we'll use the signed interpretation of those 11 bits. What would be the difference of the range of values that you can represent? Let's check it out. So I have to make this very clear here. Okay. So with the IEEE double, the range of E2 is going to be where? because e can only be as small as 0, right? That's the smallest unsigned integer you can have. But because it's biased by 1023, so that means E2 can range from negative 1023 to what? The largest value you can represent using 11 bits is 1020. No, I take it back. It is 2047 itself. And then you have to subtract 1023 from it. So the positive end is 1024. So you can specify an exponent of 2 that is going from negative 1023 to 1024. I double tapped the 2. Okay. So tax proposal to use signed 11 bits exponent will have a range of, what do you think that's going to look like? Well, think of this, okay? Number wheel, right? Except we have 11 bits. So what is going to be the most negative value we can represent when we have 11 bits? Now, to work out this problem, all you have to do is to think about what is the most negative value when we only have 3 bits. When we only have 3 bits, the most negative value we can have is negative 4. Okay? And 4 turns out to be 2 to the power of 2, right? So with 11 bits, what do you think is going to be the most negative value we can represent? Negative 2 to the power of 10. It's only off by 1 in terms of the width of the whole thing. So it would be negative 24. What about the most positive side? It's going to be something that's really close to 1024, but it's going to be off by 1 because 0 is non-negative. 1023. Okay. Well, you can see how my proposal is not really going to change the range all that much. But then you don't have to deal with that minus 1023 nonsense. So my speculation is whoever came up with the IEEE double precision floating point number format was not a computer scientist. Would you be surprised? Why would you be surprised? What is IEEE? What does IEEE stand for? I mean, we have used that word acronym many times today, and nobody bothered to ask, what is IEEE? That's not its name. There we go. It's the Institute of Electrical and Electronics. What do you think is the next word? Engineers. Engineers, okay? Oh, okay, there you go. Well, I'm only reading this part here. So I think that's why they did not use the signed representation. I really think that is the reason. Because they could have done it in a different way. So this is already in signed representation, and then the rest of the bits is really just a quantity that they can use signed representation again, which makes it very clean, right? Because you don't have to deal with that one extra signed bit on its own and a fraction of mantissa bits and stuff like that. But anyway, that's the standard. It is a well-accepted standard. And the question is, how well accepted is this standard? Is it only in software? Because we can certainly change software. No, because all your i7 processors have a floating point unit that can do floating point calculations. And guess which format they deal with? The IEEE double precision format. So it's a standard that is pretty much, I wouldn't say it is set in stone, but it certainly is set in silicon. Which comes pretty close to set in stone. I mean, just material-wise. So no, we cannot change this. Okay, tax proposal will never go through with the IEEE. All right, so we have a lab today. Okay, so we do have lab activity today. So I'm going to release it right away. Okay, what is today's date? 21st, so 25th. Hmm?
26 instead of 25th next Tuesday.
Oh, okay. I can fix that later. Might as well do it now.
Could I have the code for this one?
Hmm? Sorry?
The code for this one? Could I have the code for this one?
Double.
Double?
Yep. Yep, it's just double.
Thank you.
Yep.